In this section, we begin our study of galaxies in general, but we'll begin by looking at our own galaxy called the Milky Way galaxy. Just to give you some idea of the distances involved here, our sun is basically 1 astronomical unit away from Earth. It takes like 8 minutes from the sun to get to us, so we say that the sun is 8 light minutes away. The nearest star, Proxima Centauri, is 4 light years away. In other words, it takes 4 years for the light from that sun to get to us. If we go further out, the nearest galaxy, other galaxy than our own, the Andromeda galaxy, is 2.5 million light years away. So we're talking here about huge distances. But let's go back to our own galaxy, which is called the Milky Way galaxy. This is an artist's conception of what our galaxy looks like from the outside on top. Obviously, I cannot give you a picture of our galaxy because no one has been outside the galaxy, but it is similar to the Andromeda galaxy that we saw in the previous slide. It's what's called a spiral galaxy, and the Earth itself is 8 kiloparsecs away from the center of the galaxy. Just to review what a kiloparsec is, 1 parsec is 3.26 light years. So 8 kiloparsecs is about 26,000 light years. That's how far away we are from the center of our galaxy, 26,000 light years. Harlow Shapley studied our galaxy and tried to come up with a model of what it looks like. And in 1970, he concluded that our galaxy, our sun, is not at the center of the galaxy, that it's actually somewhere on the spiral arms near the edge of the galaxy. On the bottom, we see a picture of the galaxy from the inside, from Earth, as we look toward the center. This is us looking from Earth toward the center of the galaxy, looking this way. This is what we see. We see a lot of stars in that direction. So this is a top view of our galaxy. As I mentioned, it's a spiral galaxy. We are about 8 kiloparsecs away. The whole galaxy itself is about 30 kiloparsecs across, or about 100,000 light years across. Our sun takes about 250 million years to make one complete orbit around the center of the galaxy. So to go around once like this, it takes 250 million years. Given that the sun is roughly 4.5 billion years old, it has thus far made about 18 orbits around the center of our galaxy. How do we find distances to galaxies? Basically, we use the Cepheid variable stars in distant galaxies. These stars, during their lifetime, there comes a period when their brightness fluctuates. And we can see this fluctuation. It's very bright. And the period tells us their apparent brightness. There are two types of these variable stars called RR Lyrae stars and Cepheids. RR Lyrae stars have essentially the same luminosity curve with periods from about half a day to 1 day. Cepheid variable stars have periods a little bit longer, from about 1 to 100 days. In any case, the rate at which they oscillate enables us to find their actual luminosities. Then we can use this formula. Once we know the apparent luminosity and the actual luminosity of a star, we can use that formula to calculate the distance of the star, which is right here in this.
Most normal galaxies contain a class of stars that act like beacons to help determine the distance to the star, and hence to the galaxy. First, the pulsation period of a Cepheid variable star is used to infer the absolute brightness of the star. Then, comparing this to the apparent brightness, which is easily measured, astronomers can determine the distance to the star. This yardstick then provides an estimate of the distance from Earth to the distant galaxy housing the Cepheid star.
Formula. This is a view of the Milky Way galaxy as seen from Earth. And again, we're looking toward the center of the galaxy. And normally, because the galaxy blocks anything beyond it, we cannot see other galaxies in this direction. In the early 20th century, the existence of other galaxies was unknown. Our Milky Way was the universe at that point. But there were other things in the sky which were kind of nebulous. They were called nebulae. They were fuzzy. Light from these galaxies always appears fuzzy and diffuse due to the vast separation between the sun and these galaxies. In other words, we cannot really see a star, a separate star in this galaxy, unless its brightness is fluctuating. So therefore, galaxies are kind of difficult to observe, even with good telescope. But technology is advanced to the point where we have found as many galaxies as there are stars in our Milky Way, which is about 100 billion. So on the left, we see a little map of the universe from our own Milky Way. We see the sun there, and we see all these other galaxies that are fairly close by, and we find the distance to these galaxies using Cepheid variable method. We can use Cepheid variables to measure the distances to other galaxies. Cepheid's luminosity is proportional to its period, so if we know how rapidly it brightens and dims, we know how much energy it emits. If we see a Cepheid another variable, we measure its period, determine its luminosity, and calculate its distance. And the distance between galaxies is huge. M100 galaxy is about 17 million parsecs away. So here you see another galaxy, us here observing another galaxy, and we're observing a Cepheid variable star in another galaxy, and we can estimate the distance to that star. We estimate that there are approximately 100 billion other galaxies in the universe. So if we look at these stars where the luminosity is varying, we can see that the period of the stars tells us their absolute luminosity. So if we look, for example, and find the period to be this much, approximately 5 or so, we can see that the absolute luminosity is around a little bit under 4. And once we know the absolute luminosity and the apparent luminosity, the difference between those two actually tells us the distance to the star by using this formula. D is the distance to that star.